All right, so like I was saying, we're going to do some trig integrals today, and some of them you'll be familiar with, some of them you will not. This is one that you should be very familiar with already, how to do this. How do we go about sine to the n or cosine to the n if the n value is an odd number? What can we do with this? We should write it as an integral of sine x times sine squared x squared dx. And why do we want to do that? What are we going to do with the sine squared x? Yeah, we're going to turn the sine squared into 1 minus cosine squared x squared dx, and then we're going to make a u substitution, right? So these ones should be familiar to you. We'll let u equal cosine x, right? And then du will be negative sine x dx, and we'll need a negative and we'll need a negative. And what do we end up with? We end up with the opposite of the integral of 1 minus u squared du, right? And if we go through and distribute that all out, we should end up with 1 plus 2u squared, sorry, minus 2u squared. Sorry, I think I don't know what happened. It crashed there for a second. All right. So, like I was saying, that shouldn't be a plus 2u, it should be a minus 2u squared. And then a plus u to the fourth du, and we'll integrate that to get what? U minus 2/3 u cubed plus u to the fifth over 5 plus our constant. And if we distribute the minus sign through, we can do that if we want, or we don't have to, but place the u's, negative cosine x plus 2/3 cosine cubed x minus cosine to the fifth of x over 5, and minus a constant's the same as plus a constant. We'll just write plus c. Everybody good with that? And if we had cosine to the fifth, what would we do? We'd separate into cosine and cosine to the fourth, and then we'd rewrite the cosine to the fourth in terms of sine and do the substitution with u equals sine. Everybody good there? So anytime it's to the fifth power or seventh power or any odd power, you can separate it out and just do a u sub. Good or no? Okay. All right. What about if the power is even? What can we do if the power is even? Split up half of it. I don't know what that means. What does that mean? Split up half of it. Okay, one thing we can do, we can make it cosine squared times cosine squared. But why are we doing that? What's that going to do for us, Adrian? So if you're saying you want to make one of those 1 minus sine squared, problem with that is if I make one of those 1 minus sine squared, and I let u equal sine x, well, then I need to have du equals cosine x, and I don't have just cosine, I have cosine squared x, so that's going to end up being a problem. So any other thoughts about that? If I were to make it 1 minus sine squared x squared, then there's no cosine if I were to make u equal to sine x. So it's a good idea, Nick, but that's not going to work out either. And yeah, that's correct, Ryan. We need to use the power reducing formula, right? So we have a power reducing formula. It's on your trig sheets. You should have it memorized. The power reducing for cosine squared x is 1/2 of 1 plus cosine 2x. So we've got that times itself, right? Squared dx. And so that's going to get rid of all these powers. Well, not all the powers, but some of the powers. The 1/2 squared is a 1/4, which can be pulled outside the integral. So we have 1/4 the integral of 1 plus cosine 2x squared, or 1 plus 2 cosine 2x plus cosine squared 2x. And 2 of the 3 pieces of that are really easy to deal with, right? So the 1 just becomes x, right? And the 2 cosine 2x, what does that integrate to become? Should just be the sine of 2x, right? Good. Okay. And then plus our integral of cosine squared 2x. Well, what can I do with cosine squared 2x, you think? Probably need to use the power reducing formula another time. So first off, I'm going to distribute that 1/4. So I got x over 4 plus sine 2x over 4 plus 1/4 of the integral. And then the power reducing formula on cosine squared 2x is going to be basically the same. We're going to have a 1/2, and then it's going to be 1 plus cosine of doubling that angle would give us 4x dx. Everybody good with that or no? So we have 1/8, pull the 1/2 out, and then the 1 is just an x, and then the cosine of 4x becomes what? What's the integral of cosine of 4x? Should be 1/4 sine 4x. And I'm out of room there. I should have a plus a c down there. Plus c. And then if we just simplify all this out, we're going to have an x over 4 plus an x over 8, which is going to be 3x over 8. We've still got sine 2x over 4. And then we've got 1/32 of sine 4x, so sine 4x over 32. Plus a constant. Good or no? So if you don't remember the power reducing formulas, you usually just need to know them for sine squared and cosine squared. For cosine squared, it's 1/2 of 1 plus cosine 2x, and for sine squared, it's the same thing except a minus, 1/2 1 minus cosine 2x. So know your power reducing formulas. It'll help you to anti-differentiate any single trig function, sine or cosine, that's being raised to an even power. Everybody good there? Any questions there? Any issues with that? All right. What if we've got multiple trig functions in there? So sine to the m, cosine to the n. As long as one of them is odd, what should we be able to do? If one of them is odd, we should be able to break it up and just do a u substitution. So this should become an integral of sine x times another sine x, which we'll write as 1 minus cosine squared x, and then times cosine squared x dx. So what's the u sub we're going to use? We're going to let u equal cosine x with du equal to negative sine x dx. So put a negative inside, put a negative outside. And what does this become? It becomes the opposite of the integral of 1 minus u squared times u squared. So 1 minus u squared times u squared ought to be u squared minus u to the fourth du. Everybody good with that? Everybody agree with that? Hopefully so. And then the u squared ought to become, if I bring that negative back in, negative u cubed over 3 plus u to the fifth over 5 plus our constant, and then just resub. Negative cosine cubed x over 3 plus cosine to the fifth x over 5 plus your constant. Good or no? The 1? Oh, the 1, well, this is 1 minus u squared, right? Times u squared, Nick? So 1 minus u squared times u squared, I just distributed the u squared in. It's cosine squared minus cosine to the fourth here. Okay. All right, so what about this one then? This time the odd power is on the cosine, so we'll leave one cosine. And then we'll have sine to the fourth, and then the other cosine squared that's left will become a 1 minus sine squared x dx. And we'll do the substitution with u equal to sine x this time. And then du is equal to cosine x dx. Good or no? So sine to the fourth minus sine to the sixth ought to be u to the fourth minus u to the sixth du. So u to the fifth over 5 minus u to the seventh over 7 plus our constant, or sine to the fifth over 5 minus sine to the seventh over 7 plus our constant. Good or no? So odd powers on our trig functions makes it a lot easier. You don't have to worry about power reducing. Everybody good or no? Y'all asleep? All right, Ashley is good. Nobody else though? Okay. The other 21 of you are lost. Oh, also Molly is good. Excellent. All right, what if they are both even? What are we going to do? If they're both even, what should we do? I don't know what you mean by split the cosine. You're saying make it cosine times cosine? If we make it cosine times cosine, there's not going to be a u sub. So yeah, we're going to need to use the power reducing formulas. So both of them have a 1/2 out in front. So I should be able to put a 1/4 out in front of this whole thing, because sine squared 1 is 1/2 of 1 minus cosine 2x, and the cosine squared is 1/2 of 1 plus cosine 2x. So we should be able to rewrite that as this. Everybody good with that? And then we'll just distribute and work through it from there. So oops, I don't know why I wrote a cosine squared x there, sorry. I think I said cosine 2x. But so if we distribute that through, the 1 times the cosine 2x is a positive cosine 2x, and the 1 times the negative cosine 2x is a negative cosine 2x, so those cancel out. And we end up with 1 minus cosine squared 2x dx in there. And so the integral of the 1 is very easy, right? We got 1/4 times x minus, and then how are we going to deal with cosine squared 2x? That ought to be an integral of 1/2 times exactly power reducing again, so that'll become 1 plus cosine 4x dx. So we've now got 1/4 x, and then if we distribute the 1/4 through, we got minus 1/8, and our integral of 1 there is just x, and then we've got an integral of cosine 4x, which ought to be what? Plus sine 4x over 4, plus our constant, gives us x over 4 minus x over 8 is just x over 8, and then minus sine 4x over 32 plus c. Don't forget plus c. It'd be a real shame that if on the quiz tomorrow, when we have a quiz on partial fraction decomposition integrals, that you forget your plus c after doing all that hard work. Oh wait, no, that's not what the quiz is on, sorry. And maybe it will be, even though we haven't learned it. That'll be fun. Like a test to see what you already know. That'll be exciting. All right. What if I had something like sine to the 10th of x? Some really god-awful even power up there. It'd be cool if we could find a way to deal with any power integral. Okay. So we're going to see if we can use integration by parts to come up with a formula that will allow us to integrate sine or cosine to any power. And we're going to use integration by parts for it. So what we're going to do, I'm going to sort of guide us through this, is we're going to start with letting dv just equal sine of x, because it's really easy to integrate just sine of x. True? What would v be if, sorry, sine of x dx. What would v be if dv is sine x dx? Should just be negative cosine x. All right, so if that's my dv, what's my u need to be then? What's left of this if I've taken out one of the sines and the dx? What's left of sine? Sine to the n minus 1, exactly. Sine to the n minus 1 of x. And so then what's du going to be? Well, du ought to be, this is u, right? Sine x is u to the n minus 1, so that ought to be n minus 1 times sine to the n minus 2 of x times the derivative of sine, which would be cosine of x dx. Everybody good with that being the derivative of sine to the n minus 1? N minus 1 times sine to the n minus 2 of x times cosine x dx. Good or no? Nick, it's sine to the n minus 1 in the first place because, well, suppose this was sine to the 7th of x that I started with, and I took out a sine of x. Well, what's left? It's sine to the 6th of x, right? Whatever that n is minus the 1. Yeah? Good with that or no? All right. We're going to try something here because I'm going to need to write a lot on this page, and it's going to have to get smaller and more legible. I'm going to see if I can flip my laptop around and use it like this, and it's going to probably screw up the zoom completely, but let's see. You guys all still hear me and still see the screen?
Yes.
What?
Yes.
Yes? Okay, perfect. All right, so if we're using integration by parts here, we're going to end up with, first off, u times v, right? I'm on the eraser, though. It's going to be really annoying if I start writing and it's the eraser. So this integral should be equal to u times v, which ought to be negative cosine x sine to the n minus 1 of x, and then minus an integral of v du. So there's going to be a minus. In fact, let me, I can't use my keyboard anymore. It means I have to actually erase things. So there's going to be a minus sign, right? So I can apply this minus sign to this minus sign and make that a plus. And then it's going to be a v du. So that's cosine x, it's n minus 1, it's sine to the n minus 2, and it's another cosine x. So part of that's a constant. What part of that's a constant? The n minus 1. So yeah, so I'm going to put a n minus 1 out in front of my integral. And I'm going to be left with cosine squared x times sine to the n minus 2 of x dx. Everybody good with that so far? All right, cool. So how am I going to deal with this cosine squared of x times sine to the n minus 2 of x? Any thoughts on that? Anybody see a good trick to use there? I guess that's a no. All right, here's what we're going to do. We're going to turn that cosine squared into a 1 minus sine squared. So we still got negative cosine x sine to the n minus 1 of x plus the n minus 1, all now times the integral of 1 minus sine squared x times the sine to the n minus 2 of x dx. No, it doesn't actually depend on whether n is odd or even. What we can do here will work either way. So now what I'm going to do is I'm going to distribute this sine to the n minus 2 of x to both the 1 and to the minus sine squared x. And at the same time, as I do that, what I'm planning on doing is I'm going to split this integral up into two separate ones, right, using plus or minus, right? So that's one of our rules, is if I have a plus or a minus within it, I can split them up. So if I distribute the sine to the n minus 2 to the 1 and to the sine squared, I'm just going to have one term minus another term inside the integral, which could be split into two different integrals. And as we do that, we're going to remember to apply the constant that's out in front to both of them. So this is going to become negative cosine x sine to the n minus 1 of x plus n minus 1 times the integral of, so the sine to the n minus 2 times the 1 is just sine to the n minus 2 of x. And then we'll put our dx there. Then we're going to have a minus sign right in between them, right? Because it's sine to the n minus 2 minus this thing being multiplied. So we'll put minus, and then it's n minus 1 times the integral of what's sine squared of x times sine to the n minus 2 of x. No. That is not correct, Darius. Yeah, it should just be sine to the n of x dx, right? Because if we have the same base, the base is sine, right? And I'm being raised to the power of 2 and to the power of n minus 2. If I'm multiplying them together, you just add the exponents, right? N minus 2 plus 2 should just become n. All right. And so what do we notice here? What do we end up with as part of our integral? We end up with part of the original, right? So we can say that this is all equal to the integral of sine to the n of x dx, right? I mean, it's all equal to what we started with. So all of this is sine to the n of x dx. So if I take this n minus 1 integrals of sine to the n of x dx and add it to the other side of my equals sign, I should get a nice little formula here. Well, it's not going to be finished yet, but it's going to say something like negative cosine x sine to the n minus 1 of x plus n minus 1 integrals of sine to the n minus 2 of x dx is equal to, so if I have one of these over here, right, and I add to it the n minus 1 of them, what do I have of them? I'd have n of them, exactly. So I have n integrals of sine to the n of x dx. And so what do I then need to do to just solve for the sine to the n of x? I just need to divide everything by n. So we'll end up with the integral of sine to the n of x dx ought to be equal to negative cosine x sine to the n minus 1 of x over n plus, remembering that n is just a constant, I can divide the constant out in front, that n minus 1 by the n, integrals of sine to the n minus 2 of x dx. 1 second. And so this formula right here for the integral of sine to the n of x, we call a, that's not the letter I meant to write. It's called a reduction formula. And we'll notice that what happens with this, if I were to try and plug in, let's say, sine to the 10th of n, if I was trying to integrate that, I'd end up with negative cosine x sine to the 9th of x divided by 10 plus 10 minus 1, so 9/10 of the integral of sine to the 8th of x dx, which isn't great because I still have an integral of sine to the 8th dx, or sine to the 8th of x dx. But how would I be able to deal with the integral of sine to the 8th of x dx? I could just go back in and use this formula, except with n being 8. And what would I end up with? I'd end up with negative cosine x sine to the 7th of x over 7 plus 6/7 of sine to the 6th of x. And to figure out the integral of sine to the 6th of x, I'd just go back and I could do it again and again and again until I got down to the sine to the 0 of x, which would just be a 1, which would integrate to an x. And if I had an odd power, suppose I started with a 9th power, well, I'd eventually get down to just a sine to the 1st power, and I could just simply integrate that. Everybody see sort of how that would work? Hopefully. There's more differences between, I mean, it's very similar between sine and cosine. You don't need to memorize these, Molly. I'll probably have you write out and prove the cosine one. Well, in fact, I certainly will on your homework sheet that has to do with all of this trig stuff. But you don't need to memorize them. If you want to, that's great. It'll help you. But there's always other ways to do it, right? If you have sine to the 6th of x, you can always, use the power reducing on that to turn them into sine. Sine squared times sine squared times sine squared, and then power reduce them and deal with it that way. But it's a helpful formula that you should just kind of know exists and know how it came to be. Yeah, don't need to memorize though. So let's see if we can use it once and get it to work. We're just going to do it with sine to the 6th of x. So for sine to the 6th of x, we're just going to use the formula. So the formula says sine to the n, in our case, sine to the 6th, should equal negative cosine x sine to the n minus 1 of x, all divided by n, so 6, plus our n minus 1, which is 6 minus 1, or 5, divided by n, integrals of sine to the 4th of x dx. Everybody good with that so far? Which should then become negative cosine x sine to the 5th x over 6 plus 5/6 times, and then now we're going to do the same thing with the sine to the 4th integral. Right, so that should become negative cosine x sine cubed x over 4 plus 3/4 the integral of sine squared x. Good or no? Which should be negative cosine x sine to the 5th x over 6 minus 5/24 of cosine x sine cubed x, and then that should be plus 15/24 times the integral of sine squared of x dx. Good or no? So far good or not? So then this should become negative cosine x sine to the 5th of x over 6 minus 5/24 cosine x sine cubed x. So then we're going to have plus 15/24. I guess I could have reduced that fraction, but let's reduce it now so we don't have to worry about it later. What does that reduce to? 15/24. Divide a 3 out of both of them, right? 5/8. And 5/8 will then be times what? Should be cosine x negative cosine x sine x over 2 plus 1/2 the integral of sine to the 0 of x, which is just 1 dx. Good or not? And our final answer then should be negative cosine x sine to the 5th of x over 6 minus 5/24 cosine x sine cubed x minus 5/16 cosine x sine x, or sine x cosine x if you prefer. And then plus 5/16 of x plus a constant. So it's a little bit of work, but it's probably better than the alternative of having to go through and deal with power reducing formulas over and over again. So we should be able to apply the reduction formula to anything. And yeah, that was Aiden. Anywhere along the way, yeah, with the sine squared, you could have just used the power reducing formula there if you'd wanted to. You'd get, I don't think you'd end up with the exact same looking thing. You might, but it'd be equivalent to the same answer. So it'd be fine either way. Everybody good or no? All right, let's talk about what to do if we have tangents and secants, because these are integrals that pop up fairly often also. So if you have tangent to the m, secant to the n of x, and the n value, so the power on the secant, is even, you can always separate out one secant squared from everything else. So I can make this the integral of tangent to the 6th of x, secant squared x dx, and then convert all the other secants, which will always be, an even power of secant. If I had an even power here and I separate off one secant square, if I convert the rest of them into tangents, this becomes the integral of tangent to the 6th of x times 1 plus tangent squared of x, using one of those Pythagorean trig identities, times secant squared x dx. We can then just use a u substitution here. So what do we want to let u equal? We'll let u equal what should u be? Better at math? Yeah, I agree also. What should u be? Yeah, no, not tangent squared. U should just be tangent x, because what's the derivative of tangent x? Secant squared x dx, right? So there's my du, and then everything else can be in terms of u. So this becomes an integral of u to the sixth times 1 plus u squared du, or an integral of u to the sixth. That looks horrible. Plus u to the eighth du, or u to the seventh over 7 plus u to the ninth over 9 plus a constant, or tangent to the seventh x over 7 plus tangent to the ninth x over 9 plus your constant. And hopefully you see that no matter what value we have on the tangent, as long as the secant power is even, I should be able to separate off the secant squared, turn all the other secant squareds into tangent squareds, and then distribute the tangents together and put it all in terms of a simple function in terms of u. Everybody see that? Any questions there? Any issues with that? All right, what if the power on the tangent is odd? Now I know this one has an even power on the secant, so we could use the secant method for this one too. But if the power on the tangent is odd, then you should be able to separate out a singular secant. Sorry, not a singular secant, a singular secant x tangent x. So what we're going to do is we're going to write this out as an integral of tangent to the fourth of x, secant to the fifth of x, times secant x tangent x dx. And the reason we're doing that is because this time the substitution that we're going to make is u is equal to secant x. So I pulled one of the tangents out, which is leaving me with an even power on the tangent. And so we know that tangent squared is equal to secant squared minus 1. So this ought to become secant squared x minus 1 squared times secant to the fifth of x times secant x tangent x dx. And now we can make the substitution that u is equal to secant x, because everything is in terms of secant except for one little piece, which is the derivative of the secant. Good or no? Any issues with that? Any questions on that? Okay, so let's do the substitution. If u is secant, this becomes an integral of u squared minus 1 squared times u to the fifth, and then secant x tangent x dx is du. And if we distribute all that through, u to the second minus 1 squared is u to the fourth times u to the fifth is u to the ninth. And then we've got a minus 2u squared in there. So minus 2u to the seventh as I distribute the u to the fifth through. And a plus 1 times u to the fifth is plus u to the fifth du. And now it can easily be integrated. So u to the 10th over 10 minus u to the 8th over 4, if we simplify that out, right? And then plus u to the 6th over 6 plus our constant. Replace everything with the secant. So we got secant to the 10th over 10 minus secant to the 8th over 4 plus secant to the 6th over 6 plus our constant. Everybody good or no? You guys are awfully quiet in the chat. Nobody's saying anything, so I just want to make sure you guys are all following along, all good. You are all still there, right? My Zoom hasn't just died and I'm just like sitting here lecturing for no reason. Okay, all right. Well, I know you're a slow writer, Adrian, but that's why I post the notes so that you can, come back to it later. Yes, Nick. Anytime you see an integral that follows one of those two patterns, yeah. And for example, on this one, like I said, we had both an odd power on the tangent and an even power on the secant. So you could have done this one either way. Your answer will look very different, whichever way you do it. But that's fine. I'll do the work to make sure that your answer is the same as whichever answer I got, and I'll follow through your work to check and make sure it's done correctly. So, all right. Now, for any other cases, so basically any cases where the power on the tangent is not odd and the power on the secant is not even. So, if we have if we got an even power on the tangent and an odd power on the secant, we're going to need, most of the time, one of these two integrals. So we should already know the integral of tangent, right? What's the integral of tangent? We did a simple u substitution to figure that one out the other day, right? And I said, probably helpful if you just memorize it, right? We said we'll let u equal cosine, so du is negative sine, and we did the negatives, and we said this is negative natural log absolute value of cosine x plus a constant. And I think it was Nick said, can't that be natural log absolute value secant also? Yes, it can be. So either one of those would be fine. But what about this one? Secant x. This one's got a little trick to it. And so we're going to learn the little trick, and then you're going to memorize the integral of secant. So in order to find the integral of secant x, what you're going to do, and it doesn't seem like it makes any sense, but it makes perfect sense. You're going to multiply by secant x plus tangent x over secant x plus tangent x. Okay. So then we're going to do a u sub for this. We're going to u sub out secant x plus tangent x. So what will du be? It ought to be secant x tangent x plus secant squared x. And if you look at now what we've got in the numerator, that's a secant squared x, right? And that's a secant x tangent x times a dx. So we actually have that exact du value in our numerator. Everybody see that? Yeah, no, maybe. Okay, so the integral of du over u is just natural log absolute value u plus your constant, or natural log absolute value of secant x plus tangent x plus a constant. So this is another integral that you're going to want to have memorized. Okay. Integral of secant is natural log absolute value secant plus tangent plus a constant. Good or no? All right. So let's see if we can integrate tangent cubed of x. So any thoughts on how we might want to start that? I guess that's a no. So what we'll do is we're going to separate this out into an integral of tangent x times tangent squared x. So anytime you got trig functions and it doesn't follow one of the set patterns, just kind of play around with the trig functions and see what happens. I can turn tangent squared x into secant squared x minus 1, right? Anybody see a good u substitution there that we could use? Or no? All right, if I let u equal tangent x, I need to have a secant squared x dx, but I don't have a secant squared x minus 1 dx, right, Adrian? So it's a good thought, but it's not actually what we're going to need to do. You shouldn't see a simple u sub to use there. Now we might note that if we just had this without the minus 1, tangent x times secant squared x dx, we could then sub out u equals tangent and have du there. But I don't have that. I have that minus 1. So what can I do to remedy that problem? Yeah, if I distribute it, actually, that's right. We're going to end up with tangent x secant squared x dx as one integral, and then minus an integral of tangent x dx. And so we'll note that this tangent x secant squared x, we can do our u sub, u equals tangent du equals secant squared x dx. And we integrate now u du. And what's the integral of negative tangent x? Well, that ought to be positive natural log absolute value cosine x. And if we integrate u, we've got u squared over 2 plus natural log absolute value cosine x. Now that I've done all my integration, I'll put a constant there. And u is tangent, so tangent squared x over 2 plus natural log absolute value of cosine x plus your constant. Good or no? So I got to get a little bit creative with some of these. What are we looking at? 4 or 5 minutes left here, huh? All right. I think we're going to have to stop there because the next problem is going to take us more than 5 minutes to get through, and I don't want to. It's probably going to take me 15 minutes to get Zoom to working anyway, to get back into my second period. If I go over here, I'm going to be super late to their class. So, Adrian, you said, could I have sub secant x out also? Yeah, if I'd subbed out secant x, then we'd have secant x as u and du as secant x tangent x. That'd be fine also. Your answer would have looked slightly differently, right? You would have ended up with secant squared x over 2 rather than the tangent squared x over 2. But that would end up being the same thing. They're equivalent to each other, or they differ by a constant. So, and